So we're starting a whole new little section today, and it's actually really fun. It'll probably take us 2 classes to go over. Maybe we'll get through it tonight, but typically it takes a couple. And so what we're going to talk about is an important concept. Some of you have probably already completed labs about this, coordinate systems and projections. But there are some really important things to know about how maps are made. A lot of this you don't have to actually do a lot of, but there's some really important kind of decisions to make and things to know about how maps are warped to fit onto a flat screen or a flat piece of paper. And so that's really what we're going to be talking about. And if you're going to systematically make a scale diagram of the world, then you're going to have to also find a way to identify where on a piece of paper matches a certain place on the world, right? So there's your piece of paper and the world. Next week, I don't have any globes with me tonight, but that's okay. It'll work tonight. But next week we'll actually have I'll have some globes, and you might want to have a ball with you if you're watching. So if you're watching next week, you're going to want to have a ball so that you can kind of look at it and think about how you would take that round ball, as in the earth, and squash it flat to put it on a piece of paper. So we're going to have to go through a few sort of concepts here. The first concept is, okay, how do we determine where things are on the world? Then we have to determine, and in order to do that, we actually have to figure out what shape the world is. That turns out is actually really important. So what shape is the world, and how do we find things on it? Once we know where things are on the world, how do we transfer that to something that we can write on a piece of paper? And that's what we call a coordinate system. And so we're going to have the system of coordinates, just like a graph, a Cartesian graph like you made in middle school. Only ours will have a few more dimensions and will be round. So we'll have to get the coordinate system, and then once we know where things are and we have a systematic way of locating them on our planet, we have to figure out how we take that coordinate system, that piece of graph paper, essentially, that we've wrapped around the globe, and press it flat onto a map. So that's the process that we're going to walk through over the next tonight and probably the following week. Now, you will need something, and before I forget, let me share my screen. We'll get there from here. Present to everyone. There we go. And I'm going to scoot you down here. Right now it's just me and Zach. So, the attendance code for today is 6015, and I did not create an attendance thingy for you guys, so I'll do that right now. So 6015. And if you're wanting to follow along with me with what I'm going to be doing, you'll want to, let's see, today's the 1st, right? So if you want to follow me, you're going to need some data. And you're going to want the data later anyway. And the topic today is coordinate systems. And this will be due next Thursday. Okay. All right. So what was the number again? 6015. And you are going to need some data from the printer. You're also going to use this data in your next problem set. So it'll be handy to have. And So there's a link to the practice data folder. And the two layers that you need are the world data and the Tissot indicatrix zip files. So you need these two things right there, world data and Tissot indicatrix. I'm going to go ahead and download those to my folder and get them going. And since we're doing this on my computer today, you get to see me in my face, which is different. You usually don't get to see me when I'm sharing my screen. Okay, so I'm going to make a new folder called Coordinate Systems. And I'm going to put my world data and my Tissot indicatrix data. And it'll be super fun. And don't forget that you need to unzip those files. All right. Okay, so I've got you there, and Zach, I can see, in fact, everyone will be able to see anything that you write here, so feel free to ask questions as you go. I'm going to, I've got ArcGIS already open, so if you need to open it, you might want to do that. Remember, if it's already open, you'll need to refresh to see any new folders. And I'm going to add the following layers. So first I want my country SDC and my lat long SDC. So that looks a little weird. And then in the Tissot indicatrix, the very first geodatabase, you want the Tissot ellipses. And I'm going to hide my catalog, and I'm going to zoom in a little bit. And I'm going to manipulate my view a little bit so that I can see things a little better. I want my latitude and longitude lines to stop being that horrible color. So I'm going to make them 0.4, and I'll give them a nice light gray. They don't need to be so overbearing. Ah, much better. And then, of course, I've got the country layer. I'll make the Tissot ellipses a little different, so they're a little clearer. Now, just to give you a little sense of what you're looking at here, I'm going to put the Tissot ellipses on top too. I'm going to change the projection for my map to one that hopefully won't crash my computer. And you may want to do this too, because it will help you sort of think about the concepts that we're going to be talking about. So to change the projection for my data frame, I'm going to right click on layers and choose properties. And I'm going to scroll all the way up here. We're going to now finally explain the difference between a geographic and a projected coordinate system over the next couple classes. But for right now, let's collapse it and collapse geographic and expand projected coordinate systems, and then world. And there's a projection called, where is it? The world from space. It's weirdly enough in the T's. So the world from space. So I'm going to select that, and when it says, are you sure? I'm going to say yes, and it's going to draw the world as it would appear from space. And it is actually does require quite a lot of computing power, so it does take a little bit. And we're just going to use the default settings there. So I'm going to let it draw. And then the Tissot ellipses will come up. I'm not going to manipulate this a lot. I'm mostly just going to be talking about it. So while that, you want to, so the Tissot layer that you want are the Tissot ellipses. Come on. And it actually doesn't, I don't think it matters whether you use the 9.3 one or the other one. They'll both be readable, but I use the one without the 9.3. It's referring to a prior version of ArcMap. So it's this, so you want to expand the geodatabase right here, and inside is the Tissot ellipses. And that's the one you want. And I do want to see if anybody is trying to sign on. They might have just decided to go home, which is understandable. None of them appear to be online. Okay, that's fine. All right, so what we're gonna do now, oh, my Tissot ellipses didn't draw. Oh, come on, I want my ellipses to draw. Doo-doo. I have probably interrupted it. So drawing a lot long. And come on. If the computers are too sluggish to run this, to do this particular thing, there is another website we can use that will work a little easier. And the computing happens on their side, so perhaps, there we go. There are the ellipses. Excellent. Okay. So the Tissot ellipses that we added, notice when I look at this Earth from space view, that the ellipses are no longer ellipses, or they're a special kind of ellipse, which is a circle. So those ellipses are special, specially designed shapes that allow us to see how distortion works when we squash our map flat. So that's what we're gonna use to take a look at some of these distortion issues that you run into when you squash your map flat. Okay, so let's go over here. And I've got it. That's not the right one. That's not the right one. I have it here. There we go. So I've got some slides here that will help to explain what we're talking about here. So today we're going to talk a little bit about a concept about a field of study actually called geodesy. And geodesy is a really interesting science, and it's essentially the science of measuring the Earth's size and shape, and then creating models, computer models of the Earth. It's a highly mathematical and geometrical activity, and so you know, some mathematicians. It you know, involves lots of mathematicians. We have one fairly well-known geodesist here in Maine named Joe Zakis, who was on the faculty at University of Maine at Augusta, but is now a provost there. So I don't think he's doing too much research in geodesy. But geodesists do stuff like take measurements from space and satellites of the Earth's gravitational field and its the shape of the Earth. It's not, you know, it's not just a perfectly round, smooth ball. It's actually kind of lumpy and misshapen somewhat. This is a gross exaggeration, actually, of the Earth's gravitational field. And so if we're going to make maps that are accurate, that aren't distorted so much that they're unusable, we need to make an accurate shape, you know, of the Earth. And so, so the Earth is lumpy, and it's lumpy in certain really specific ways. And so we need to figure out how we take this round, lumpy potato and squash it flat onto a map. I'm not going to get into this. Just know that people have the idea of, you know, how the Earth is shaped has been evolving over a long time. You know, there was a sort of early notion that the Earth was flat. And there's the sort of myth that, what's his name? Christopher Columbus thought the Earth was flat. He did not. Or no, discovered that the Earth was round. He did not discover that the Earth was round. And people of his day did not believe that the Earth was flat. What they didn't know, though, was how big it was. And they had difficulty measuring it. And so really the challenge over many, many centuries has been how to measure the Earth and to determine its shape accurately. And so the Greeks, Pythagoras and Aristotle, both understood that the Earth was at least kind of spherical, and they noticed things in the heavens moving in circular orbits. And then Eratosthenes actually calculated, and I won't get into how he did it, but he calculated the circumference of the Earth to it's about, what is it, 22,000 nautical miles, something like that. And he calculated it to be about 20,000 nautical miles. And so people have been doing this kind of thing for a long time. Isaac Newton figured out that due to centrifugal force, that the Earth would be squashed. And there's a really important reason for why the Earth would be squashed. It's because the Earth is not solid. So think about it like this. If you had, let's say you had a ball of ice cream, it's really cold ice cream. But ice cream, even when it's cold, is still kind of malleable. And then you put that ice cream into a vat of whatever that weird stuff is that they use at Dairy Queen to put a shell on that ball, right? And then break it up so that you've got the shell floating on top of kind of melty ice cream. And there's a gumball in the middle of the ice cream. That's sort of like what the Earth is like. There's a core, a hard iron core, and then between the core and what we know of as the surface of the Earth is essentially molten rock. It is plastic in the sense that it is malleable, and floating literally on top of the mantle, which is what that mushy part is, floating on top of that mantle are all the pieces of the crust. And that includes the continental plates, which are relatively light and float higher and made mostly of granitic rock. And then there's the basalt that forms most of the ocean basins, and that's heavier and that sinks lower, and that's why they're lower in elevation. And then the material of the Earth is all distributed in funky patterns. And the denser the material, the more gravity there is, and the closer that water and atmosphere is pulled towards the Earth in those places, and in other places where it's less dense, it's sort of spooging out. So the rock itself is moving constantly. And then the water and the atmosphere are all subject to a variety of forces. And one of those forces is the flinging out, the centripetal force, the flinging out force of the rotation of the Earth, and Isaac Newton figured that out. And so he rightly surmised, and this is true, that the Earth's axis from north to south is shorter than it is from east to west across the equator. In fact, the distribution of material around the Earth is such that there's more water to the south than there is to the north, and that water is flung out slightly more. So there's the widest part of the Earth is just to the south of the equator, not at the equator itself. This is, of course, a gross overgeneralization of that flattening, but we call this model of the Earth, it's mathematically calculated and modeled in a computer, call that an ellipsoid. And then when we add in all these other things, right? So the gravitational anomalies lead to lumps in the material of the Earth. and distributions of different densities of rock and so forth also determine lumps. We get this bumpy thing. And so geodesists create these models in computers that, as best they can, approximate the shape of the Earth. There are lots of different geoids. There are lots of different kinds of models, and we're going to use different ones depending on the kind of maps that we're making. So this lumpy ball is called a geoid. And so you'll often hear these terms, ellipsoid and geoid, being used, sometimes sort of interchangeably. But the ellipsoid refers to the part of the model that looks at the semi-major and semi-minor axes of the Earth, so the bulging and the squashing of the Earth based on its rotational spin. And then the ellipsoid, so that's the ellipsoid, sorry. And then the geoid is adding on top of the sort of perfect ellipsoid, the bumpiness. Does that make sense, Zach, since you're the only one here to make sense to? Hopefully you're still there and interested. And okay, good. Feel free to toss out some questions. So geoids, there's a really important element of geoids and ellipsoids. So a geoid, oh, this is a really crappy picture. That is just a crappy picture. Let me see. So best fit geoid. I'm looking for a better picture. So good. Okay, here we go. This is a good picture, except it's too, oh, no, there it goes. So here's an image. Maybe I'll even post it wherever it went. There we go. So here's an image. And this is from a page that's sort of TMI about geoids. It's a little more information than you guys really need. But it shows you the concept. So geodesists take these ellipsoids and then they make them round and bumpy, and they do so in a way that best fits the Earth for whatever kind of map they're trying to make. And so in this example, and geoids, as you might guess, are hugely complex, right? It's really, really hard to make a good geoid because they're so complicated, and you can't just, an ellipsoid, it's described by a very simple equation. But a geoid has to have many, many, many different equations based on measurements of the real Earth. And so geodesists create these models of the Earth as best they can. And some geoids are made to fit a certain area of the Earth. So this geoid, the red line here, fits this particular area of the real Earth pretty well. Other parts of the Earth, not so much. So, for instance, we use a geoid based on a geoid that is for North America. It's called the North American datum. And a datum is, it's based on the center of the ellipsoid that the geoid is based on, and it's pinned to the Earth at the center of mass of the, or center of the geographic center of the North America. And so the NAD, the NAD geoid fits North America great, but you wouldn't want to use the NAD system for something in Japan, right? Because it's not made to fit there. And so a lot of your locations will be off, both in the vertical dimension and in the horizontal dimension. Because a geoid not only determines where your coordinates are going to lie on the Earth, on the surface of the Earth, but you also have to measure above and below that surface of the Earth to get all three dimensions. All right, so let's see where, there we are. So geoids are made to best fit certain areas of the world. And there are a few common geoids that we use specifically for world maps. So the World Geodetic Survey, WGS 1984, there's a geoid for that, and that's for the entire world. It's not particularly great in every place, but it fits the entire world, meh, okay. But at that scale, when you're making a whole big, huge map, that's good enough. Okay, so that's just a quickie little introduction to how geodesists create models of the Earth, right? So that's this first step, is that we had to figure out how the Earth is shaped, why it's shaped like that, measure it, and make a model of it. So now we've got models that we can use. Once we've got a model, we have to figure out where things are on the Earth, right? And how do we usually do that, Zach? No pressure or anything, being the only student tonight. I'll be back in the lab next week. So how do we usually locate things on the Earth? What do we do? If somebody wants you, yeah, we use coordinates. If somebody wants you somewhere, they have to tell you reference locations, and those locations need to be pinned to real places, right? And so we use coordinates. Latitude and longitude is one of the most common, but it's not even close to the only one. But for now, let's assume we're talking about latitude and longitude. So latitude and longitude is very similar to a piece of graph paper that is wrapped around our geoid. It's probably easier to think of it as wrapped around an ellipsoid like this. And just to pretend like the Earth isn't bumpy for now. But we have to find a way to measure coordinates on that system. And this isn't the right, well, we'll get there, I'll find it. So we have to figure out a way to measure locations on that coordinate system. We also have to measure, so we need a horizontal coordinate system, which allows us to measure things, around the surface of the Earth in what we think of as the XY direction. But we also need another set of reference points that measure distance. You can think of it as from the center of the Earth, but more often from the surface of the Earth, and in the case of a geoid, the surface of the geoid. So the geoid is designed so that you can lay a coordinate system on it, around it, wrap it in a coordinate system, just as you would in this ellipsoid here, and have that coordinate system be referenced to real locations on the planet, and then measure along each of the lines in this graph paper that you're wrapping around the world. There's one problem with that, which is that each of these lines is not a straight line. So when you were making graphs in 4th grade, right, you were making graphs on graph paper with straight lines. And so when we wrap these lines around the globe, they are curved, and that creates a problem. So how do we fix that problem? How do we resolve that issue? And we'll get there. Oh, right, so datums. Oh, I haven't gotten there yet. Okay. Coordinate systems. So, okay, so a coordinate system needs to have some key things. It has to have reference points, right? So an origin, that's your 0, 0 coordinate in when you were making graphs in 4th grade, right? So it's that place where the two lines meet, that's your 0, 0. So you need to have that reference point. Since we're working in 3 dimensions, not only do we need a horizontal reference point, we also need a reference point in the vertical dimension, so the 3rd dimension. And we need some way to determine where, relative to those reference points, the left, right, or north, south, and up, down, where we are, how far you are. So you have to grade, cut into gradients each of those lines. The locations that are origins, so that the starting points, are known as datums. And so often people actually call a geoid a datum. And what they're referring to is its, what do you call it? Starting points, locations, the reference points. Okay, this you understand already. This is the X and Y coordinates, right? So remember that the X is the horizontal dimension and the Y is the vertical dimension. The X is the horizontal dimension and the Y is the vertical dimension. That's going to be really important. Okay, and I'm going to get a different set of, so that's the measuring the Earth. I'm missing, I'm going to get a different set of diagrams that are better. Ah, there it is. Okay. All right. Okay, so here's what the Cartesian coordinate system looks like when it's just all squares, right? And this is with all 3 dimensions. And so you've got the X and Y and the Z coordinate. And when you're pinning it to the Earth, the Z coordinate is going from the center of the Earth out into space, right? And so we have those beginning reference points. The equator, that's this right here, is referred to as the x-axis, and that's known as 0 latitude. That is the x-axis. Let me repeat that 412,000 times. Latitude is the x-coordinate. I'm sorry, no, latitude is the y-coordinate. Oh my God, I already said it wrong. Latitude is the y-coordinate. And so its latitude at the equator is 0, right? And so it is the x-axis, just as the x-axis is all the places that have a 0 y on our usual Cartesian grid. And then we have this prime meridian, which is right here. And the prime meridian is all the places that have 0 longitude. That is our y-axis. So the prime meridian is the y-axis. The equator is the x-axis. Now, we're going to use that and reference where we are. Let me go back over here to my map, and I'm going to show you how to view the latitude and longitude lines a little bit differently, so that we can see where our equator and prime meridian are. So I'm going to double click that baby right there, the lat long layer, and I'm going to choose categories and unique values, and value is fine. We'll keep everything there, so value is fine. And instead of adding all values, I'm going to just click this Add Values button, and if I scroll around, it looks like I'm missing my zeros, but I want my zeros, so I'm going to hit Complete List. 0 is now there, and I'll click that one, and that's the only one I want. I'm going to click OK. So 0 now can have, that's 0 degrees latitude, which is the equator, and 0 degrees longitude, which is the prime meridian, and they can now have a different color. So I'm going to give them a big fat red line. And all other values, that's here, the checkbox is checked. I'm going to click that patch right there, and I'm going to make them 0.4, pretty small, and I'm going to make them gray. And I'll click OK. Click OK. I want to zoom out a little bit while this is drawing. Just one little step, and I'm going to let it draw. And there's my equator coming in, and my prime meridian is drawing now. And eventually, I'm not going to touch any of the buttons, and eventually the Tissot indicatrix ellipses will draw as well. So here we can see the special, those two special lines, those two special, so the, yeah, I'm not going to touch it. So the equator is our x-axis, just like on a Cartesian grid, and the prime meridian is our y-axis, only we've wrapped them around the globe. So, and we've sort of pinched the tops of our graphs and the bottoms of our graph together so that all the meridians, all the lines going from north to south all meet at the poles. So that's how we turn this into what's known as a spherical geometric system, spherical geometry. So let's look at how we measure. If we have a location on the Earth that we want to measure where we are, and that's it right there. So we've got that location. What we need to do is find out how we name each of this. So this is called a parallel, and this is called a meridian. How we name our parallels and meridians. Okay, so a line of constant longitude is a meridian, and a line of constant latitude is a parallel. All meridians meet at the poles. All parallels never meet because they're parallel. And we have to figure out then how to locate a location, a place on this coordinate system from this origin, the 0, 0 point, right? Now, one thing that's really important to remember is that longitude is east-west. Longitude is east-west, and that means that it is the x-coordinate. It's confusing because we usually say latitude, longitude in that order, and we usually say x, y in that order. So it's reversed. So longitude is the x-coordinate. Pretty much every quiz you take from now till the end of the semester, you will have that question, and you'll probably get it wrong several times. So if you memorize, I'm not really big on memorization, but if you memorize anything, you probably want to memorize that longitude is x, latitude is y. Longitude is x, latitude is y. So our x-coordinate is going to be how far we are east or west of the prime meridian. And our latitude coordinate is going to be how far north or south we are of the equator. Okay, so we've got that location that we've got to figure out where we are. And here, I think what I'm going to do, I'm going to actually start, how can I, here we go. I'm going to actually do this presentation because it builds itself in. You can unmute yourself and tell me if you have questions while I'm doing this. So there's our location, and I want to figure out where it is, right? There's this imaginary post that goes from pole to pole, right? It's the post that the globe spins on, and we can think of that as the central axis. And so when we want to figure out what our latitude is, how far we are above or below the equator, we measure in angle between the center of the Earth and the equator, and then the center of the Earth and our parallel. So think about that for a minute. If you take your hands and you make a little sort of pie shape out of them, a little wedge shape out of them, and you imagine that the post is going through the middle of your wrists, and you were to spin your wrists around that post, your fingers, so your lower finger, your lower hand would be describing an arc that would be at the equator, and whatever your upper hand, wherever your upper hand is, that's your parallel, right? So it's that angle. Let me present again. So that's your latitude, is that angle. So when you hear latitude expressed in degrees, that's what it means. So our latitude in this case is 45 degrees north, and it's our y coordinate. So for longitude, that's how far east or west we are of the prime meridian. And the prime meridian is here. This north-south line, right, is our origin for our x coordinate. And so that's measured in the angle between the prime meridian, the center of the Earth, that post, and my meridian. So that's that angle right there. And so in this case, it's longitude 50 west, and that's our x coordinate. All right. So does that make sense, Zach, the way the coordinates are measured in degrees that are angles? So that's why we measure them in degrees, minutes, and seconds. Excellent. So some students have some trouble wrapping their head around this. The primary thing that they have trouble wrapping their head around is that latitude is the y coordinate, and using, sort of thinking through your the way that you measure the angles is really helpful. So here, I'll make myself a little bigger on the screen. So there we go. So for latitude, right, we were going like this. And so it was an angle like that to describe our parallel. With longitude, the post is going between our wrists, and one hand is at the prime meridian and the other hand is at our meridian. If we move our wrists up and down the post, we're going to describe essentially an orange wedge, right? It's the same thing you would cut out of an orange, right? And we'll actually, that shape will come up in some interesting places later. Now, the other thing that's really important about coordinate systems, well, among the many things, are the quadrants. So latitude and longitude, so the computer doesn't really like to read coordinates in east, west, north, south, right? And so we have to identify the coordinates in such a way that makes it easier and less data intensive for the computer to express and to read and understand. And so latitude and longitude are typically expressed in positive or negative degrees, and degrees, minutes, and seconds. And so, we divide the world into quadrants, and here's what those quadrants look like. Let me make this a little bigger so you can see it a little better. Up you go. There we go. So the prime meridian, which runs through Greenwich, England, thank you, Europe. They essentially got to literally say where the center of the world was, because they were the ones. There was a time actually before, I forget the date, 15, 16 something, I think it's 16 something, around the time of, Isaac Newton, there were a lot of different coordinate systems around, and everybody chose their own central meridian, prime meridian. And so you know, everybody had their own, and yeah, wah-de-wah. And it made it really difficult for people, you know, navigators and so forth, to understand how to use maps, because the coordinates were not sort of measured out around the whole globe. And so explorers started to see the need to get everybody on the same page. And so the Royal Society of London established they established a number of things, but one of the things that they did was to get everybody in Europe to agree that the prime meridian was in one specific place, and they chose that to be the 0 degrees longitude. And there's some really fun books about that. I'm not going to get into that much further from there. But it's important to know that each of these quadrants is its own. Oh yeah, I wanted that down there because I want you to see that Asia is there. So each quadrant has its own positive and negative signs, right? So, and it's just like your graph paper that you used in middle school. So to the right of the prime meridian and the north of the equator, and of course that's most of Europe, you're in positive territory. And then to the west of the prime meridian is negative longitude. To the south of the equator is negative latitude. We, of course, are in this quadrant. So all longitudes in our hemisphere are negative. All longitudes in North America are negative. And all latitudes are positive because we're above the equator. One of the most common mistakes that GIS 1 students make, I remember doing it as a GIS 1 student myself. One of the most common mistakes that you make is you'll collect a bunch of data and you'll forget that longitude is supposed to be negative, and you type it all into your spreadsheet and you add it to a map, and all of a sudden all your points appear somewhere in Asia. And I'll never forget being like gobsmacked, why are all my points in Asia? Well, I forgot to put the negative sign. And so it's an important thing to remember. You will forget it, but that's really key. Okay. And these are key concepts. I will post this. I will post these slides so you'll be able to see them and come back to them when you take your next quiz, because this information will be on the quiz. So the longitude is the angle between the prime meridian, the center of the Earth, and your meridian, and latitude is the y coordinate and the angle between the equator, the center of the Earth, and your parallel. All right. Any questions, Zach, or are we all good? So I think I'm going to save converting coordinates for later week. And I'm gonna come back to it. Great. I'm going to come back to it and we'll take our time and go through it piece by piece later. So, but for right now, I think what I want to do is I'm gonna switch over to another slideshow. I guess I got all kinds of slideshows going. I'm gonna have to pull them together into one. Okay, so remember, this whole process is about systematically taking a round, bumpy world and squashing it onto a flat map. We've got a model of the Earth. We took the sphere, we squashed it to make an ellipsoid, then we made it round and bumpy to make our geoid. We took a horizontal datum and wrapped it around the Earth. We also took a vertical datum, and one thing I guess I forgot to mention about the geoid, let me come back over here. So the geoid is is vaguely defined as the surface of the Earth as it would appear if there were no continents in the way of water moving. And so it's it's a sort of 0 point from which we can measure. So think about it this way. It would be much, much more difficult, for instance, if when we measured the high jump in the Olympics by measuring how far each jumper jumped from the center of the Earth. It's much more practical to measure how far they jumped from the ground, right? So we measure things from the ground. And so by creating the geoid, not only, and wrapping the coordinate system around it, not only do we choose the X and Y coordinate datums, so the beginning points, right, the origin of our X and Y coordinates, we also have to decide where is 0. There are a few different kinds of 0. We typically use in this area the North American vertical datum as our 0, but that's, believe it or not the same as tidal 0, but it's generally about where sea level is supposed to be. And so the surface of that geoid is essentially as though the Earth were covered with water and there were no continents in the way. And that allows us to measure altitude from that geoid. So you might have thought, oh, well, altitude is measured from, from a round, smooth, 0 point. It's not. It's measured from the surface of that geoid. And the bumps in the geoid, these are exaggerated here, but the bumps in the geoid are pretty large. In fact, there are parts of the Earth that are, many, many meters farther from the center of the Earth than on the opposite, side than others. So it is truly very bumpy. And so if we tried to measure it from a sort of globally defined 0 without making the bumpiness of it, we'd end up with really impractical difficulties where 0 would be way deep underground in some places and way above ground in others. So that's why we use this geoid in this way. Okay, so we've got our geoid, we've got a horizontal datum, we've got a vertical datum, and we've got a coordinate system, and we wrapped our coordinate system around the Earth, and we worked out a way to locate things on the Earth. So the next step is that we've got to put those points onto a map. And most of our maps are flat. We only have one kind of map that isn't flat, and that's a globe, right? And it looks like that, right? So this map is the way a globe looks, right? And here we can see none of our Tissot ellipses are distorted, as if you imagine this as a three-dimensional object, right? So this is what the real world sort of looks like. And somehow we have to turn it into a map that's a little more practical to use, right? It's really difficult to take a globe, for instance, on a road trip and refer to it in your car. And so there's an process that we have to undertake of squashing the Earth to fit. And if we just do it willy-nilly, which we do when we like make a little folk map, when we draw directions to our house, right? We're just doing it willy-nilly. The result won't be to scale, and we need our maps to be to scale. Sometimes we need them to be very, very much to scale. So really precisely to scale. So we need really good systematic ways of taking this round blob and going, squashing it flat. So that's what I'm going to do next. Now I'm going to remove my projection. We've been looking at the round globe now. I'm going to right-click on the word layers and choose properties. And I'm going to go back to the geographic coordinate system. So I'm going to expand that. For right now, I just want to use a world geographic coordinate system. I'll use WGS 1984. I mentioned that earlier. So, and if we look down here, it's based on a spheroid. So this is a geoid based on a spheroid with these dimensions. And this spheroid and its related geoid were developed as part of, in fact, these are refinements, each of these other ones, but that was based on satellite data that was collected and recalculated for a new geoid of the Earth in 1984 after satellite measurements became possible. So I'm going to choose that one and apply it. And I'm going to zoom so we can see the whole thing. So this is a map. If we just took the coordinates off the Earth and then just put them on a piece of graph paper, right? So notice that all of my little squares are square, right? But what do you notice about the Tissot ellipses here, Zach? What's going on with these Tissot ellipses? There's something funky. They're distorted, and they're distorted in really specific ways. So, so there's no distortion right along the equator, or very little distortion right along the equator. But the further we get away from the equator, our Tissot ellipses become more and more distorted. And you can see, of course, that the landforms behind them are also distorted. And so this process introduces difficulties. So if we were to make our maps, make maps that we wanted to use, for instance, navigating around Antarctica, this would be a deeply, deeply impractical way to make that map. We need to find another way of looking at the Earth such that it allows us to systematically and retaining, relative scale as best we can, squash it so that the area that we're interested in the planet is least distorted. And there's no one way to do that. So if we think about, the ball, here's my apple, right? I'm just eating this apple. So if I take this apple and I think, oh, okay, if my apple peel was stretchy or bendy, right? There's any number of ways I can stretch or bend my apple peel, right? Or a balloon. I have done this, but then I realized I'm allergic to balloons, so I don't do this anymore. But if you take a balloon and, blow it up, a spherical balloon, and blow it up, and then draw the Earth on it and pop it, you have this piece of rubber, right? And there's any number of ways you can stretch it and squash it and smush it to make it flat. And whichever area you pick to stretch or squash least, other parts of the rubber will be stretched and smushed more. So that brings us to this this problem of using a coordinate system, this geographic coordinate system with just graph paper, just squares. How do we take that coordinate system and stretch it and squash it and control the distortion, minimize the distortion for the things that we want to use or measure, and allow other things to be distorted? There's no way to make a flat map of a round world without distortion. And there have been very poorly informed people who somehow thought there was a way to do that, but there's not. There's no one definitive way to smush. So that process is called projection. So projection is the process of smushing and squashing and so forth the world. And there are four ways in which the world can get squished and squashed, stretched and squashed. Four things that get distorted. One is, this should be larger. I want that to be bigger text. Yeah. So one way that happens, and if we look over here at our map, is direction, right? So, and direction is not too bad in this map if you're only going north or south. But if you want to figure out what the direction is directly from, say, Moscow to Cartagena, the angle there is going to be, come on in. Yeah, the angle there is going to be different from what it is in the real world. And that's because of this introduced distortion. And so this whole sort of can of worms that we're just about to open will manage that. Then, of course, area, we can see area. And the Tissot indicatrix, these ellipses are really great for showing area and shape distortion. So you can see that area is greatly distorted in the northern and southern latitudes in this map. And then near the equator, of course, there's no distortion at all in the area, the size. And then, of course, distance, right? So if we look at this, so the distance between, say, New York and Moscow is greatly, greatly exaggerated in this map. But the distance between, say, Ecuador and Indonesia is not distorted at all. That would be roughly correct because there's no distortion along the equator in this map. And then finally, of course, shape. If you're distorting the other things, direction, area, and distance, then you're going to distort shape. And so, and I don't even have to say anything. You can look at the Tissot indicatrix and see how shape can be distorted. Okay, so we're stuck with this problem, and we need to be able to fix it. And there's no one way that will preserve all these things, direction, area, distance, and shape. There's no way to preserve them all. And so we build projections, and this is where I'm going to leave you. We build projections that preserve one or two of them. Occasionally we'll sort of approximate three, but even that is you know, asking for trouble. So we build projections that preserve direction, area, shape, or distance, because we can never preserve all of them. And so we have special names for these projections. An azimuthal projection is one that preserves shape, direction, I'm sorry. An equal area, it's obvious what that preserves. Equidistant, obvious what that preserves. And then conformal preserves shape. And so we're going to be talking about how you choose different projections in order to minimize distortion for the type of map that you need, right? So if we've been making choropleth maps, and so an equal area map is perfect for a choropleth map because it's all about the area covered by each color. But if you're navigating, say, a jetliner, you're going to want an azimuthal map so that when you point your plane somewhere, you get where you think you're going. So that's where I'm going to leave it for tonight. Do you have any questions for me? I'm happy to answer them. We're gonna we're gonna come back to this next week, and we'll talk about all the different ways. Let's see, when will problem set 2 be assigned? Problem set 2 I'll probably wait until next week to assign it. We have a couple more. It's probably gonna be 2 weeks before you have everything you need to know about problem set 2. So there's going to be there'll be 3 parts, but 2 parts that you haven't quite finished yet. So one is about projections, and the other is making a reference map. And so we need to go over some things for you to make your reference map, and next week we'll work on the projection thing. So what we'll do is, oh, the class page says it's due this week. Oh, do you mean the syllabus? Someone set 2 is not due this week. Oh, it does say due. Yeah, no, it's not due. Don't worry about that. I feeks. Thanks for bringing that to my attention. I'll delete it right now. Yeah, it will all be revealed. I'll never assign you something. It won't ever be, you know. One thing that happens is if I make an assignment that I haven't taught you enough about yet, people panic and like all my office hours fill up and everybody wants me to just instruct them on, and I'm like, but we haven't done that in class yet. So I have to wait until you have a sort of critical mass of stuff that you know how to do before I assign it. And we're just not quite there yet. All right. Well, thanks, Zach, for being my student, and hi to all the rest of you. And I'm sorry I couldn't be in the lab tonight. And I will see you all next week. Have a great week.